first, we're going to spend today talking about waves, and we're going to talk about different types of waves. Some waves being mechanical, some waves specifically being the types of waves such as transverse and longitudinal. We're going to talk about those terms. We're going to talk about a pulse wave and a periodic wave. We're going to talk about frequency, speed, these terms that have to do with the rate at which the wave is traveling. And they're different things, speed and frequency.
Are we doing a lab segment?
We are doing a lab segment. And then we're going to talk about energy and amplitude, how those two things are related. Okay, so let's take a quick look at some definitions first. We need to know some terms. The first term, and I left these blank because I want you guys to maybe give me a little feedback. What would you think is a wave if you had to define a wave? And it's a very general term because there are so many definitions of a wave. Like, what is the context that I'm speaking of? I'm in physics, but when you hear wave, what do you think of, you know? Katie?
Something outside some motion, constant motion.
Something is under some sort of constant motion, okay?
Something that like goes up and down, like it's not constant, but it fluctuates in and out at a constant rate.
Okay, something that involves some sort of fluctuation. I like that, Frank.
I think about like multiple waves, like a wave and then the wave and they affect each other almost.
Yeah, how waves propagate or affect one another, how they interfere. We can have constructive or destructive.
I think of like sound waves or like ocean waves.
So you drop the pebble in a pond, just a ripple effect like that, or the waves literally in the ocean as it crashes, you see it. Now obviously those waves are gravitationally pulled, but waves in general, the wakes in the ocean are like waves. And then what was the first one you said? Sound, right?
Sound waves.
Yeah, it's sound waves, right? I think of sound. And then, we go on to this whole idea of there are many other types of waves, so bless you as well. And in general, what we want to say here is that when we're looking at a wave specifically, we're looking at some sort of a disturbance, okay? And we're generally talking about the motion that's involved in that disturbance. So that's a general definition of a wave. Not that you need to know those exact words, but it involves some disturbance. Because you can't have a wave without some sort of source of the wave. Waves don't just occur on their own. For example, if there's an earthquake, the source of the waves for an earthquake?
Tectonic plates.
Yeah, tectonic plates moving against one another. Okay, that creates some sort of pressure differential, which as a result causes this earthquake. But if it's under the ocean, we see a tsunami. If it's in a fault line on the west coast, we just feel the vibrations. Now, those disturbances cause these periodic or pulse behavior. So I'm going to jump to the bottom. We'll get back to the mechanical meaning in a second. When we talk about periodic and pulse, what does it mean? Periodic versus pulse. What do you think?
Periodic, it's like on the schedule kind of.
Yes, exactly. Something that's periodic would be like, okay, every day 2 we do this. That's periodic. Every day 2. Or once a week you go to get lunch at this place. That's a periodic nature. So something that's periodic, it has some sort of predicted schedule. So if we're talking about waves that are periodic now, specifically waves, versus waves that are pulses, what do you think when you hear pulse?
A heart. It's like
Yeah, you think of like a heartbeat or a pulse, like the murmur of your heart. Now, each of those individual murmurs is a pulse. So when you hear about a pulse wave, you could think of one individual wave. Many pulse waves in a row makes a periodic wave. Again, a pulse wave is one single wave that's been generated, whereas a periodic wave is many pulse waves in some sort of predictable fashion. So you want to grab the windows? Let's see. Yeah, Frank, why don't you grab the end of this one? Yeah. All right. So just hold it like that with your hand around it. So they're trying to distort this thinking, but hold it above the desk, surface of the desk. All right. So you send one pulse wave. How would you send one pulse wave, Frank?
just like doing that.
Okay, that's simple, right? Now, what's happening to that wave that you send?
Going back and forth.
It's going back and forth. Now, that has to do with the fact that the wave itself is being transmitted back due to the end. This is like a fixed end, we might call it. If this end was around like a pole and it was tied, that end could lift up and it could move. And you've seen that with like ropes before. So what would a periodic wave be then? Yeah, you're constantly sending wave. Now this is a little bit tough here. Let me grab this and see if maybe make it longer, it'd be a little easier. So if I go a little bit further and stretch this out. So why don't you do that, Frank? Yes, there you go. So that's one, it's a little more obvious when it's longer, sorry. So you send one pulse wave there. Now if you keep doing it, keep generating waves, Frank, you eventually get what's called a standing wave if you do it actually continuously. Now, if you can generate the same wave over and over again, you're going to see you're going to get like this like standing wave now. Yeah, see how it like starts to become a standing wave there? This in the middle there where it's not moving, that's called the nodes. These are antinodes. And it's kind of cool actually, and you see this before, this has to do with harmonic frequencies. And the actual wave that's being propagated is not moving right here. These ends were doing this, right? That's what was happening the whole time, what you can see, right? This is where it was stationary. There's a lot of cool stuff in waves. The idea though of a pulse or a periodic wave first has to do with the pulse wave being one single wave, periodic is generating a source that generates continuously. Now, for these waves to actually travel, they have to have what's called a medium. And we'll talk about when waves don't need a medium, but these waves that we were just using, sorry, right there, needed a medium. And a medium is what it travels through. So it's not obvious with this, right? With these waves right here from the slinky that we just used. But if I were talking about something like sound waves, how do you hear what I'm saying right now? Through what medium? Through what medium do you hear what I'm saying?
Your ears.
Okay.
The air, the sound waves.
The air and your ears both, really. The medium is what the wave travels through. How does the sound wave go from my mouth to your brain? How are you interpreting it? Well, I am disturbing the molecules around my mouth, I guess. I'm sending out some sort of a sound wave with a vibration from my vocal cord. That's then propagating throughout all of these different waves. We'll talk about why it propagates this way versus this way. But it's propagating outward and it's disturbing the following molecules, which are disturbing the following ones, until it gets to your ear. And your eardrum is then disturbed, and that signal that your eardrum picks up is converted into some sort of a sound that you can make sense of. And obviously when you're a baby, you haven't learned like the language yet, you haven't understood everything, so you don't make sense of sound really that well. But as babies progress, they start to even understand what things mean without even being able to talk. They can still understand it because they're starting to make sense of it. So the medium through which we communicate is air, really. Okay, the air is vibrated into your eardrum, which interprets the sound. How would you, if you were, how many people fish in here? So like to fish, all right. How do you know where you want to fish? What do you use?
Like the radar.
Yeah, so, but what, if it's underwater?
Sonar.
It's sonar. And sonar is really just sound waves. And sound actually travels quite fast in water, faster than it does in air. Believe it or not, sound travels faster in water than in air. And when you send out sonar waves, you're doing the same thing. You're disturbing the medium. What's the medium there? What's the medium for sonar?
Water.
Water. What are the waves traveling through? Water. When you're fishing and using sonar waves. Okay, when you're speaking, the medium is air.
Is that what
Okay.
dolphins do?
Is that what?
Is that what like dolphins do?
Fish definitely use underwater sound. Yeah, absolutely. To communicate in general. I don't know specifically about dolphins, but they definitely make noises, dolphins. But usually they're out of the water when we hear them. But they definitely communicate underwater as well using sonar. Anyone know a lot about amphibians fishing? Is it like a receiver, you think, or some sort? It's possible, yeah. Anybody ever seen the movie, I think it's Tremors?
Oh, with the weird
Creatures
monsters
that come out of the ground?
Yeah.
You know how they communicate? They communicate through these like sonar waves or these sound waves that they send out. They can talk, but it's like these high screech, different like pitch frequencies.
That's a classic.
It is a classic. So the medium, if we were to define it formally, would be the material through which the wave travels. And the material through which it travels, which is what we were talking about, giving examples. Now, mechanical waves require a medium that is what's called deformable. Mechanical waves require a deformable medium. For example, sound, we'll go back to. Water is deformable. The air we breathe, this atmosphere that we're on Earth, is deformable because we can cause the molecules to vibrate and move. outer space is empty space. There's nothing there, right? There's no medium. So in outer space, you can take your helmet off and scream as loud as you want, and no sound is going to go anywhere. That's why you've heard that.
Scream in space.
Yes, exactly.
What is it?
No one can hear you scream in space.
No one's going to hear you scream in space, because you can't, literally. You can try to make as much sound as you want, but you can't now. Mind you, astronauts are in a spacesuit which acts as a little mini atmosphere, if you think about it, or mini medium with air in it. So they can talk to their ship because they have a little mic that sends a little, signal so they can hear it, and then they can speak back to the microphone. But if they took off the mask itself, right, and they were in empty space and there was no air around it, they could not vibrate any molecules in the air around them, so you could not scream. So mechanical waves are things that require that. What would be an example of something that's not a mechanical wave? It's not. And give me a rationale, these two. Yeah? Did you put your hand down or no?
Well, because I originally just thought oh, ocean waves. But I would say no.
Water is the deformable medium there for sure. There's one example that would be a little bit easy to think about if you consider what I just gave as an example. That in outer space sound doesn't transmit.
Light?
Light, very good. Okay, light. Light can go from the sun to the earth, and it's traveling through outer space, so clearly it does not require a deformable medium. Light is not a mechanical wave. Okay, light is an example of saying it's not a mechanical wave. It can travel through outer space and still make it to Earth. All right, now that we've got these definitions down, let's talk about types of waves. So the first type of wave we're going to take a look at is a transverse wave. Okay, a transverse wave. And we're going to do it with the slinky because this is really easy to use as an example. But how many people have ever done some sort of jump rope before? Okay. If you're holding a jump rope on either end, and you sit at one end and you go like this with the jump rope, you would see waves like this, right? Propagate. You would literally see the rope kind of dance. Now, if the other person was holding the other end versus it being free, it's a different result. If the other end is free and I'm going like this, you might propagate, but it kind of dies out toward the end. It might flutter and then that's it. If somebody's holding, you might get like a standing wave. Like me and Frank, when we were going like this, it was called a standing wave. You kept seeing that oscillation back and forth. Here, what's the source of the wave in the diagram? What's the source of the wave? Source. Tell it.
The blade?
Yeah, the blade. The blade is vibrating, so somebody maybe flick the blade and let go, and it starts to vibrate. Or there's some sort of a machine usually causing a vibration. Your engine in a car is usually the source of some sort of oscillation or vibration or wave. As the engine rotates, it is cyclical, it's periodic, right? You're thinking about the speed, the axles rotating as you're driving the car. Think about the pistons moving up and down in this oscillatory motion. They turn a little crank arm that sits there and rotates. All these vibrations are caused by some source. So it's important to recognize that you don't have vibrations without a source of vibration. Things don't just start suddenly vibrating on their own. It doesn't happen that way. You need some sort of a source of this oscillation or wave. So for a transverse wave, we're thinking about the fact that, you know what? The actual location on the wave is oscillating up and down. But the wave itself is moving left to right. So if you go back to the example of the slinky, class, grab the items. Okay, if you just look at a few single waves, and you just look at waves where you oscillate up and down like this, the wave is traveling back and forth, left to right, but which way is this oscillating? This is oscillating up and down. So we say that this is transverse. Where have you heard the term transverse before? Come on, folks, math. Come on, think.
Is it in
Geometry.
triangles?
Is it transverse?
Oh,
Not triangles.
transversal.
Triangles could be involved.
Transversal.
Transversal, so parallel lines traditionally. And a transversal cuts through the parallel lines. Transverse in this case has to do with the fact that the wave is traveling left to right, but the particles are vibrating up and down. Okay, so they're perpendicular to one another. That example again is when the wave does this. It goes up and down, but it's traveling left to right like that. So if we were to graph this example of the rope, and we took a look at a few, oscillations of the rope, look on the right over here. We'll see that we have the actual waveform. the waveform itself in this case, and it's funny because I was talking to Victoria Montalbano, and she's going to be in next period for the lab, and I was explaining what I wanted you guys to do in the lab, and I was talking about waves and stuff, and I said, remember this from last year? She said, yeah, I remember and everything, but it turns out that right now, remember I was saying, math, you're going to do this. That's what they're studying right now. They're studying sine, cosine, tangent, the idea of waves. And in her class, she's realizing that all this stuff with wavelength we're going to talk about, and amplitude and frequency, you're going to do a lot more than math next year. The ideas are what we're going to look at this year. We're not going to do a lot of the math behind it because you still have to learn a lot about that in your Algebra 2 class. In your Algebra 2 trig class, you're going to learn about the unit circle, you're going to learn more about your trig functions, and to understand these waves mathematically, you need to have that knowledge. So what we're going to do is we're going to identify characteristics on here real quick. So let's zoom in and take a look at this graph. So when we look at this graph right here, this symbol right here is called lambda. And that means wavelength. So right here it's given at the bottom. Okay, it means wavelength, and it's pronounced lambda. Like if you were to pronounce it phonetically, like L-A-M-B, like lamb, duh. D-A or D-U-H, duh, you know, lambda. So it's another one of our Greek symbols. Again, meaning wavelength. Now, if you look at this example, wavelength shows up in two spots, doesn't it? The top and the bottom. Well, which one is the wavelength? Which one is the correct wavelength? Or why does it show up in two spots?
Aren't they both like the correct wavelength?
Yeah, so example, in the first example at the top here, it's really the distance from the crest to the next crest, or peak to peak, some people would say, or max to max. Or you could define the wavelength to be the distance between the trough to trough, or min to min. It's the same distance overall because this is a periodic wave that continues with the exact same motion. Now, in real life, unless you have some sort of generating source that can keep this wave at this frequency, which you do, that's how you send out radio waves, that's how you listen to the radio. The source sends out that wave at the same frequency, the same wavelength, the whole time, so your antenna can receive that wave. Now, in real life, a wave that's a mechanical wave will usually die off. Is my sound continuing forever? No, it stops, right? If you were to throw a pebble in a lake, over time, what would eventually happen in the lake? It would steady itself back out. It's called dampening. The wave gets dampened. It doesn't continue forever. This example here is showing the fact that if we continue to look at a wave that is occurring over and over again, we could find the wavelength two different ways. I could find the wavelength a third way. Another definition of the wavelength, take a look, would be from here. I'll circle it in black right there, to here. The upper half is half a wave, literally. Follow the wave itself. This is half of a wave, this upper portion right here. And this is the other half of the wave. So this is one full wave. So from this black circle to this black circle could also be defined as a wavelength. Okay, but the idea of wavelength is that the longer the waves you have, the lower the frequency you have. Remember, frequency and period were inversely related. We talked about that. Frequency and period in the beginning sections here were inversely related. The longer the wave, like the longer the period, the shorter or lower the frequency. High frequency waves look like this. It's like the spikes up and down on like some sort of a radio wave signal if you were looking at it that had a high frequency. Okay, so waves that were compressed, that were squished a little bit more, that went up and down many times in this length, has a high frequency. So again, wavelength and frequency, let's jot that down, are inversely related. Just like period and frequency were inversely related. Wavelength is analogous to period. It's pretty much the same thing, except you would have to have time as your variable right here. If this axis right here was time, then the distance from here to here, although it's called the wavelength, would also be the period length if this were time. It's not time in this case, but the idea is the same. Can somebody explain what amplitude is then? Just looking at the diagram, how would you define amplitude? Because we've defined amplitude already. Remember, for a pendulum, the amplitude is the angle at which you raise it up and then let go. That's the amplitude. For a spring, it's how far you pull and let go, and then it's going to oscillate back and forth from that amplitude. What is it in the graph? How could you define it?
This is like a wild guess, but
Take it.
the distance from the point of rest or the origin or something.
Okay, so this x-axis too.
Yeah, and it's the distance from the
X-axis, that's fine.
yeah, but the point that you're picking, right, it's not gonna be any point, it's the point, of the lowest point, the one with the most distance, like you're not picking it from all
Correct,
the way
like,
to the right.
I'm not talking about here to here,
Right,
but from
well,
here to here. So what is this called?
in the middle. The distance from the x-axis on a parabola or something,
To the what? What do you want to call this?
vertex or something.
Sure, that's one way to use it. Now, for these, we have mins and maxes are the easy way to use terminology. So the distance from the midline or the x-axis to the maximum or minimum value. So we're talking about this distance here, or this distance here, or this distance here, or this distance here. They're all the same thing, right? The height of each peak is the same as the depth of each valley in this figure here. Right? Those heights are all the same because this is periodic, the motion is consistent. So this height up to here is the same as this depth. So the amplitude, easily put, is the distance from the midline to a max or a min. Either one. The perpendicular distance, if you want to write that, you can. Okay, that's what Benno was referring to. He was saying it's the point directly above or below the max or the min. So that you call that, you can call that the perpendicular distance to a max or min. Okay, this is really good terminology to know and to understand about what a wave is. Again, I'm not going to hound you on the math and the idea of, one period is what's called 2 pi in length, because you're going to see that in math class later on. So it's not something that you're going to learn just yet, but you'll see the application of it in your math class. And then if you go on to take a class next year, like AP Bio or AP Physics, where you have waves involved, that you have to use in some sort of math, that would be good for applications. All right, so again, transverse, if we reiterate, just to make sure we're clear on this, transverse, the actual vibrations of the particle are perpendicular to the wave itself. The particle was oscillating up and down. We could see that it moves up and down the whole time, but the wave was moving left to right. So what's the idea of longitudinal waves? And longitudinal waves, you really do need a slinky actually to show this. This is a tough wave to demonstrate without something that is compressible. A slinky is compressible, right? I mean, it's here, and I can compress it. It's made to be compressed, actually. In its resting state, it's compressed. Now, if I held it though and let go, is it going to be compressed? Okay, no, it's obviously not. But the idea behind, has anyone ever seen this before? The top of it catches up to the bottom beforehand. Have you ever seen that? Somebody pulled that up and ever talked about it in this class, or was it the other class? Watch what happens. Anyone have a high-speed camera? And your cell phone?
I have a slow motion.
Slow-mo camera, whatever it is, yeah. You want to just record this real quick? Just watch what happens in the slinky. It's kind of cool.
Yeah.
Don't do it yourself.
How do you press this for slow motion? It's on slow.
Wait, no, it's on.
It's on slow motion, so just.
Yeah,
just
yeah.
oh, okay.
And then you can take.
Oh, okay. It's,
Tell me when you start.
yeah. Oh wait, here we go.
Yeah, you're gonna try and get bottom slinky. Watch what's happening. Let's see who can get an idea of why it's happening. Explain why. I should really have it to rest on one side, right? Okay. Ready? Go.
That's cool.
If you watch it like real quick, you're seeing what's happening physically. You don't have to explain why, but what's physically happening. What did you see? Speak.
Basically, the
You're
whole,
going to this. Sorry.
basically the whole thing becomes one thing and like kind of pushes it down.
And then it falls right afterward. So what you're noticing is that it's pulling, the weight of the bottom that's hanging is pulling on the spring so much that there's a certain amount of force in the spring. That force is creating an acceleration greater than gravity, greater than 9.81. So the top catches up before it starts to fall actually, and then it falls kind of together. You want to can you send that to me or put in
Yeah,
Dropbox? Thank you. Maybe we'll take a look at it real quick at the end.
looks so cool.
It looks really cool. It looks like it's magic. It looks like it's suspended in the air. In slow-mo, it's really cool to see. Yeah, I've seen this on YouTube before. That's the only reason I thought of it when we were doing that. Anyway, back to the idea of compressible waves. Longitudinal waves involve motion of the wave that is no longer perpendicular to the wave itself, but parallel. So, Willow, grab the end of this. Alright, so instead this time, instead of sending a wave, we're not going to do this time, okay? Instead of sending a wave that way, what we're going to do is kind of just like, so what I want you to do in your hand, what I want you to do in your hand, you try this with the hand with the sling catch, so I'm going to demonstrate it here. It's just like this, like push and, yeah, okay? So try it again. So watch what she does here. So she's not gonna oscillate this way. She's gonna push the wave toward me. Okay, and what's happening really in this case, and it's hard to see, is you're kind of compressing the spring, which is compressing the spring after it, which is compressing the spring after it, which is propagating throughout the medium. So when you do that, you send a wave back and forth. Try it again, Willow. Try and like make it really noticeable. You know what I mean? Yeah. See that? So it's a quick impulse. That quick impulse is sending a wave that goes back and forth. This is a longitudinal wave, and the spring is compressing. So the compression and the oscillation, take a look, is horizontal because it's compressing and then it's opening. It's compressing and then it's opening. That's what's happening. So the compression and oscillation is horizontal. The wave is also horizontal. So they're moving parallel to one another in this example. Not perpendicular. Remember, this was perpendicular. And we saw the wave was literally up and down in motion, in vibration, but in motion is left to right. Whereas here, it's both left to right. Okay?
It's
Okay? So what we're going to see here, and this is actually a little bit. I don't. No, the iPad doesn't have it on here. What we're going to notice here on this one is that it's difficult to understand this graph, and let me explain what it is. Take a look at this is an example of a spring or a slinky, okay, with a fixed end on the right. If you take a look at this and you see that when you send a pulse, it's going to be compressed in certain sections and stretched in other sections. That's the only way part of it compresses, the other part of it stretches. So where it's compressed, you can think of that as a high density of coils. If the spring is compressed in one section, where it is right here at the top, you could think of this as a high density of coils right here. So the graph of density increases until you get to right here. There's the highest density. Then there becomes less and less coils. Then the coils are kind of stretched out until they're really stretched out here. And then they're compressed again, and then they're stretched. So if you look at the graph, you say, okay, this is compressed, stretched, compressed, stretched. When they're compressed, it's high density. When they're stretched, it's low density. Compressed, high density. Stretched, low density. So this is not a graph of the vertical vibrations. This really is representing compression and stretching. So you're thinking about this as like the wave is being like pushed together. So there's a lot of coils there, so it's higher up. And when they're stretched out, that's like right here, when they're stretched at x2, it's got this density down here, which is lowest. I would differ my graph to look like this personally. Because I have difficulty understanding negative density. It doesn't make sense to me mathematically. So that's probably how I would draw my graph. But the concept is the same. Okay, this is a figure out of your text. Okay, I wouldn't want to ever think about negative density. It doesn't make sense when you think about density. Density is concentration of a certain substance in a given area. How could you have negative concentration? It's not possible. It means absence of, or, you know what I mean? It's either zero or something. Can't really have negative density. So that's maybe how I would draw my graph. But the idea is the same. That you still get this periodic motion, really. Okay, but the concept that we're getting at here is that longitudinal waves, the motion of the wave was horizontal, while the vibrations were also horizontal. So the motion and the vibrations were parallel to one another. Okay, again, a good example of this, this would be sound waves. When I speak, the sound waves vibrate and causes this compression and expansion of the molecules in the air. Another example that's very easy for you to relate to. Have you ever been to like a concert or maybe an opening night at a movie where there's a really long line? Somewhere where there's a long line, a baseball game, whatever it may be. Now, imagine that the person controlling the line, whoever, whatever you call them, ticket agent, bouncer, depending on what the situation may be, says, all right, 20 of you can go in. That's 20 people in. What does the rest of the line do? Move up and wait. Now, the front of the line moves up, right? Don't they first? Then doesn't the person after them move up? And aren't there instances where somebody's like clearly just doing this on their phone and they're not even looking, and everybody's behind, like, oh, move it. Oh, sorry. And there's like a bunch of room, they have to catch up. That line is like your sink here. It's compressing and expanding and oscillating. Think about the front of the line. The front of the line kind of stretches out as the front of the line moves to empty that, to fill in that empty space. And then the next part starts to follow behind it. People don't walk like soldiers in everyday life. They're not like in tandem, right? You're not walking down the road and the person behind you is not walking directly behind you ever. It just doesn't happen that way. With a line of people, it's the same thing. Unless it's some sort of regiment, it's not going to happen where you're going to walk one after the other in step, in tandem, in sync. Okay, so you're going to get this oscillatory wave motion where people compress and then expand the space between them. So an example of this, again, would be like waiting online. Okay, waiting online somewhere where there's a long line that allows people to enter whatever the venue may be. Okay, let's take a look at a little bit of math that we're going to utilize in this section. So first, we're going to take a look at what's called the speed of the wave. The speed of the wave. And this is not the same thing as frequency. When we say the speed, we mean the speed in meters per second. If we think about our definition of speed, or in this case, velocity, we're going to call it the speed because we're not going to care about the direction, but I'm going to use velocity to derive the equation. Okay, so just bear with me. I know it's speed here, but I'm going to use the velocity equation to derive. If you think about velocity, velocity is your displacement over time. And if you think about a wave is traveling one wavelength every period. It's literally traveling a wavelength every single period. So this here, the distance traveled, is the wavelength. This is a length. What is x measured in? What are the units of x always?
Meters.
Meters. Wavelength is also measured in meters, but usually you'll hear like nanometers or micrometers, micrometers. Time is really the same thing as the period itself. Time is period. Now, period is defined as 1 over frequency. So you've got wavelength over period, or wavelength over 1 over frequency here. Wavelength over 1 over frequency. That's what that means right there. And how do you divide by a fraction? You have to multiply by the reciprocal. So you end up getting wavelength times frequency equals velocity. Okay, wavelength times frequency equals velocity. So in this problem, or this concept, think about this fact. All electromagnetic radiation travels at the same velocity. All of it does. That velocity is 3 times 10 to the 8 meters per second. Sound in air travels at 343 meters per second. It's the same velocity whether you're speaking or I'm speaking. The sound waves travel at the same velocity. You can't speed up your waves at all. You can't get your sound waves to get to me faster than I can get to you, or vice versa. But I can change the pitch of my voice and speak in like a higher pitch or a lower pitch, right? And that, what I'm changing is the frequency, omega. That little W symbol is the pitch of my voice, the frequency. Well, if I change the pitch of my voice, and this is always the same for sound, then the wavelength has to change as well. So think about this mathematically. Pick a number for velocity. Let's say 20. If the frequency were 10, the wavelength is just 2, right? But if the speed is still 20 because it's not changing, and I double the frequency, what happens to the wavelength?
1.
Yeah, so it goes from 2 to 1. So if I double the frequency, I have the wavelength. Doubling the frequency halves the wavelength. So how are they related?
Directly.
Inversely. Be careful. I know this is tough here, because you know why? They're both in the numerator, right? But they're both on the right side of the equation, and they're equal to something that is constant. Velocity of sound in air is always constant. The velocity of EM waves, which are like radio waves, gamma rays, microwaves, anything, any reception you get, infrared rays from your television remote to turn the TV on or off, they all travel at the same velocity, so this velocity is not really going to change. So a higher frequency indicates a lower wavelength. They are inversely related. We mentioned that earlier, but just to reiterate that. Okay, again, frequency and wavelength are inversely related, these two. First example. Alejandro, want to read for us, please?
The wavelength of the sound wave produced by a middle C on the trunk wave approximately 0.72 meters. If the speed of sound the speed of sound in air is 343 meters per second, find the frequency pitch of this.
So, first of all, visualize this. 0.72 meters. Isn't that kind of crazy to think about? That's the length of the sound wave. A meter is like this long. So 0.72 meters means that a sound wave is actually this long. Which is quite interesting to understand, like physically, how could that be possible in your ears interpreting? We're going to talk about size of waves and how they affect the body when we get to EM waves specifically. The speed of sound is constant, and we're trying to find out what the frequency of this is. And frequency, for those who are into music, is the pitch of the note. Okay, now we know that a middle, how many people play an instrument or sing or something of some sort? Okay. Well, if you are ever tuning, you know to use, what do you use to tune?
Tuning fork.
A tuning fork or what do they call it? Simply a tuner, or like if you're trying to get your beat, use a metronome, but it's just, is it just called a tuner for music?
They have a tuning fork, like the thing that you hit.
You actually use tuning fork in your band class?
Well,
You don't use
we
electronic?
don't tune an orchestra, we don't sound good enough for that, but yeah.
Well, you can, I mean, in general,
No,
usually
no,
you have like an actual, an oboe that has a perfect,
It's
some kind of perfect
it's
pitch.
either an oboe or a clarinet player, we usually.
You tune to one other person that has the right pitch. If you're at home practicing, say, you use a little tuner and it says sharp or flat. And when it's sharp, it's too high of a frequency, it's too many hertz. When it's flat, the needle moves to the left. This is a middle C, this is a note that you all tune on. It's a concert B flat for any sort of band. So you would use this as the whole band to tune on this note itself. So if we're trying to figure out what the actual pitch of this note is, we know we have our formula V equals omega lambda. The velocity equals frequency times wavelength. Velocity, if we want to think about it, is measured in meters per second. Wavelength is measured in meters. We'll divide those two to give us the frequency. What are my units going to be of frequency? What are my units of frequency? I'll give you a break in a minute. Let's finish this problem. What are my units of frequency here?
Waves per second.
Wait, not waves per second. Look at your units. Come on. 343. What are my units going to be for frequency?
Seconds.
Close. Very close, Ellie. Meters cancel for sure. What is it?
Millisecond.
Not milliseconds, no. It's definitely something with seconds.
Microsecond.
Hey, question for you. Look in the top right of the board. If I did this, look up please. If I did this, what does that reduce to? Definitely not x. 1 over x. Good, Emma. When I cancel things and reduce, this goes away, leaving a 1. This goes away, leaving 1 over x. So when I cancel the meters, what is left behind, guys? 1 over second and a 1 as a unit. So my units of frequency are 1 over second. What was 1 over second defined as in section 12.1 and 12.2?
Hertz.
Hertz. Very good. Hertz. Again, frequency is measured in hertz. That's what 1 over second is. But I want you to see that physically when you're doing your math. Okay, the 1 over second remains, which is hertz. I'm going to get a frequency of 476 hertz, approximately. Okay, to the nearest integer there. Okay? I'm going to pause and give you a quick second to go take a quick break. Second example here. We want to calculate the actual wavelength of an X-ray, which is a type of EM wave, and all EM waves travel at the same speed. At the end of the problem, you're given the speed is 3 times 10 to the 8 meters per second. But here you're given the frequency in megahertz. And I wanted to do this example specifically because a lot of the time when it comes to frequency, bless you, for anything on the EM spectrum, so electromagnetic waves in general, they have frequencies that range from very, very low values to very, very high values. So we're not going to have things that are going to be simple numbers. We're going to have to look at our prefixes. So we start by listing. We know that the velocity, That does not look like a V. The velocity is 3 times 10 to the 8 meters per second. So that's the velocity of EM waves in general, okay, in a vacuum in general, but we could say in general for now. And then we talk about the frequency here as 3 times 10 to the 12th megahertz. What does mega mean? Big, yes. Specifically, in physics, what does mega mean as a prefix? Anybody remember from the prefix table, mega? Well, let me give you an example. What do you got?
It's not 1,000.
It's not what? What's 1,000?
Yes, he is 1,000.
What is 1,000?
Milli.
Milli's thousandth. What's 1,000? Kilo. Remember kilogram? 1,000 grams. All right. So kilo is 1,000. Mega. If you think about data from computers, there are. This is not exactly true. There are 1,000 kilobytes in a megabyte. 1,000 megabytes in a gigabyte, 1,000 gigabytes in a terabyte. They all go by factors of 3, or 10 to the third. So, in this case, if we're looking at megahertz, it's 1,000 thousands. 1,000 thousands, which is really just a million, okay, or 10 to the 6. So mega is 10 to the 6. So for this symbol here, for the frequency, it's really 3 times 10 to the 12 times 10 to the 6 hertz. I've literally done this, and take a look at what I've done. I've replaced mega as a prefix with times 10 to the 6, which you can absolutely do. Remember that we talked about it in the very beginning of the year. If you remember the definition of every prefix, you can just replace it. So if I had kilograms, and I wanted to write it in grams, I could replace the word kilo with 10 to the third and drop it and make it grams. The same thing applies here. So what does that make it? It makes it 3 times 10 to the 18. Okay, 10 to the 12 times 10 to the 6 is 10 to the 18. So that's my actual frequency. And carry down the symbol omega the whole time. My frequency is really 3 times 10 to the 8 hertz. This was just the conversion from here to here, which is really becoming this. So there's the frequency, there's the velocity. Again, you're going to use the same formula. This portion of the year on math becomes very easy because I'm going to give you one formula and you can literally plug in from that formula or into that formula. So we start with our formula, V equals omega lambda at the top right there in red. You're solving for the wavelength, which is lambda, so it's V over omega. That is what lambda is. I'm on the top right of the board, okay? We're solving for lambda, V over omega. You're going to get a very small number. You're going to take the velocity, 3 times 10 to the 8, over the frequency of 3 times 10 to the 18. 3 over 3 is clearly 1. 10 to the 8 over 10 to the 18 is 10 to the negative 10. So the wavelength is going to become 1 times 10 to the negative 10 meters. It's a very, 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 very small wavelength. Well, X-rays are rays that need to be extremely small, not need to, but are used because they're extremely small. X-rays allow us to analyze the human body because of the size of the wavelength. And we'll talk more about radiation and things like gamma rays and rays that cause mutations, results of nuclear weapons and nuclear warfare. So we'll specifically talk about that when we get to the EM spectrum, but I want you to get an idea of this. This is really, remember nano? Nano means 10 to the negative 9. This is really 0.1 nanometers. So although X-rays have been around for a long time, the fact that it's on a nano scale has not really been addressed until more recent times when we started talking about nanotechnology. Okay, things that are on this scale, on this small of a scale. So that would be the wavelength in this example. In the last slide, just we have this time to do it, okay, we'll talk about waves and energy in general. And I'm going to make 4 points. Okay, 4 points I want you to just either jot down or understand. First, the rate at which a wave transfers energy depends on its amplitude. The rate of energy transfer depends on its amplitude. And make sense of that, please. You take a little pebble, throw it into the pond. What happens to the ripples? A little pebble. There's small ripples, right? I take a boulder and launch it into a pond, and it goes, you know, you do it like a cannonball pretty much. How big are those waves? Much bigger in amplitude because they are transmitting much more energy. Amplitude and energy. Second, the greater the amplitude, the more energy it carries in a period as well, not just the rate, okay, but in a given period. Specifically, we're going to see this. Energy is proportional to the square of the amplitude. Energy is proportional to the square of the amplitude. Okay, we'll talk about more of this next class, but that's our general conclusion there. We'll explain where that rule applies, where that idea applies.